Let's begin now. Good evening, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Networked Intelligence at the Robert Bosch Center for Cyber Physical Systems, IISc. Today's talk is by Dr. Sudarshan Mukherjee, and he will be speaking on cell-free massive MIMO in realistic LoS or NLoS channel. Dr. Sudarshan Mukherjee received BTech degree in Electronics and Communication Engineering from National Institute of Technology, Durgapur in 2011, MTech degree in Electronics and Communication Engineering from Indian Institute of Technology, Roorkee in 2013, and PhD degree in Electrical Engineering from Indian Institute of Technology, Delhi in 2017. From 2017 to 2019, he was a postdoctoral researcher with the Department of Information and Communication Engineering, DG Institute of Science and Technology, Republic of Korea. Since January 2020, he has been an assistant professor with the Electronics and Electrical Engineering Department, IIT Guwahati. His research interests include communication and signal processing using large-scale antenna systems, mobile edge computing, and ultra-dense networks. Before we move on to the talk, we would like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. I will be pasting the links in the chat box. Please do check. Finally, we request the audience to keep your microphones on silent for the duration of the talk. And for questions, you may ask Dr. Mukherjee directly or type them in the chat box, and we will moderate it with him. Over to you, Dr. Mukherjee.
Thank you, Anusri. Good afternoon, everyone. Today, I'm going to talk about cell-free massive MIMO in realistic LoS and NLoS channels. If we look at the vision for the next generation wireless technologies, what we see that there is an effort towards integrating different aspects of existing and futuristic wireless communication and networks into a single wireless network. In short, what we want is the network flexibility, and we want to integrate all the previous generations of existing heterogeneous cellular networks integrated with various enabling technologies that have been developed in the past decade and coming up even now for improving various key performance indicator requirements. And at the same time, we want to support various innovative and smart services and applications like online gaming, data processing, virtual reality, e-health monitoring, and various IoT services. If we look at the different enabling technologies that have been developed, one of them is massive MIMO systems, which essentially is a extension of the conventional MIMO systems. And in order to achieve this extension, it was suggested that we increase the number of antennas at the base station, and deploy a very large array of antennas. The original version of this traditional large-scale antenna array implementation of this large-scale antenna array at a single point is termed as cellular massive MIMO systems, which has later been evolved into a distributed, interconnected, multiple access point based deployment, which is called the cell-free massive MIMO systems. If we want to understand where exactly the cell-free massive MIMO stands in the next generation of wireless systems, we need to see exactly what type of features it can provide and where it can fit in. So the key features that cell-free massive MIMO provides, the first one is the end user proximity. In cell-free massive MIMO, we distribute the antennas that were supposed to be present at a single location across the network on multiple access points. In this way, we actually eliminate the concept of cellular boundaries and bring the access points to the far off users. So as a result, the distance between the user and the network access point decreases, and we can provide low service latency with an improved and near uniform coverage to all users. There is also the facility of interconnected multiple access points, which actually can provide coordinated user-centric transmission throughout the network for all the users. This is a specific feature which is very similar to that of network MIMO systems and can provide coordinated interference management and power control. So we can in a way say that self-free massive MIMO systems is an equivalent representation of network MIMO in densely deployed access points with joint transmissions. And finally, self-free massive MIMO can be considered to be an infrastructure for the various innovative and smart services. For example, there are already existing works which are considering various innovative services like edge computing from the perspective of self-free massive MIMO, and it has been shown that it can provide a very significant improvement in performance, whether it is in terms of the reducing the communication and computation latency, or in terms of power management. Besides that, self-free massive MIMO can also be implemented for automatic traffic control, e-health monitoring, and various other IoT and innovative services. So, in short, we can say
Dr.
that self.
Mukherjee,
Yes.
sorry to interrupt you. Could you share the slides in full screen?
Uh, okay. Just a minute.
So right now we can see two slides. Next slide
Okay.
also we can.
Okay.
Yeah, thank you.
Okay. So, in short, self-free massive MIMO can act as a infrastructure or backbone for the deployment of various services in the future wireless networks. Coming to the point of main topic of the talk, today I'm going to present my an work completed by myself and my colleague Dr. Rivu Chobra. The title of the work is Performance Analysis of Self-Free Massive MIMO Systems in LoS and NLoS Channels. It was recently published in IEEE Transactions on Vehicular Technology. There are two basic prerequisites for this work. We need some basic understandings of RF signal propagation in wireless channels, and also we need some understanding of the self-free massive MIMO systems. The contributions of this work we can summarize as twofold aspects. The first aspect is that we consider a probability-based LoS and NLoS propagation model for the channels. And secondly, we debunk the myth of uniform service or in self-free massive MIMO, or rather we can say that the uniform service is not always available in self-free massive MIMO systems, which leads to our conclusion that we need better algorithm for data detection and interference management to achieve uniform service in self-free massive MIMO at all times. Today's talk is outlined as follows. We'll first discuss the RF propagation model for wireless channels. Then we'll discuss the MIMO systems and scaling up MIMO and why we go self-free. And finally, we'll begin our discussion on self-free massive MIMO performance in realistic LoS and NLoS channels. If we want to consider signal propagation in wireless channels, then we need to first look at the characteristics of these channels. The main characteristic, or the most notable characteristic of wireless channels, is the multipath fading, which is the natural phenomena that is originating from various effects of waves being reflected, refracted, or diffracted onto various particles or various obstacles that are naturally present, or man-made obstacles that are present in the environment. That as a result, because of multipath fading, there are multiple copies of the same wave that are coinciding at the same point, which results in a variation of the channel gain with time and space, resulting in an unreliable channel. Now, if we look at the various propagation aspects, we can see that the nature of propagation links in a wireless channel is essentially can essentially be considered or divided into two main groups. The first group is the non-line of sight propagation channel, whose effects is essentially summarized as a Rayleigh distributed envelope of the channel. And the other one is line of sight channel, which consists of a line of sight component along with all other non-line of sight paths, which results in a Gaussian distributed envelope. And of course, additive white Gaussian noise is another component which is ever present. If we look at the performance of any classical modulation scheme such as BPSK or binary phase shift keying in wireless channel, and we can study the result of bit error rate performance, we'll see that if we consider the performance comparison with respect to AWGN channel, there is a significant loss in performance due to multipath feeding when we talk about Rayleigh feeding channel or the Gaussian feeding channel. However, due to the presence of line of sight component, there is a significant performance improvement when we compare the Rayleigh feeding and Gaussian feeding channel. This essentially shows that if we have a line of sight propagation link and if we don't have line of sight propagation link, there will be a significant variation in performance in wireless.
Quick
Based
question.
on that, yes.
In the previous slide,
Yes.
this mu and k seem to be defined in terms of each other.
Right.
So, so mu is actually a complex number, right? It's something times 1 plus j.
Right.
And mu is defined in terms of k, but k itself is mu squared over sigma squared. So k is also a complex number.
Oh, sorry. Actually, this should be mod of mu square. I apologize for that. But it should be mod of mu square. No, it is not the simple square. It is absolute value square.
So it's like a recursive definition. So in order to compute k, you need to do mod of mu square, which in turn you can substitute for that, and you'll have an implicit equation connecting k to k. And that's how you determine k.
Right.
I see. But normally in the Gaussian, you have the Gaussian factor k that can be controlled, right?
Actually, the definition it should have been written as mu is equal to root over of k by 2 into times k plus 1, and sigma is equal to root over of 1 by k plus 1. I just have instead of writing it that way, I have just represented k something like this.
Okay, got it. Thanks.
Hello.
Yeah, got it. Thank you. Yeah, you
Okay.
continue, please.
Okay. So if we look at the RF propagation model in the urban environment, which is the predominant area where all the cellular systems are deployed, we can see that it has, in general, two permanent source of path loss. One is the original free space path loss, which is common to all propagation links, where the path loss is proportional to the link distance between the transmitter and receiver. And of course, there is shadowing and scattering, which is essentially considered Gaussian distributed. And this shadowing and scattering, it is an excessive path loss, which essentially depends on the different types of propagation links, as well as antenna elevation angles and various other system and environment parameters. So if we want to characterize the overall average path loss in any RF propagation environment, we can actually say that it can be summarized as the sum of different path loss for different propagation environments multiplied with their individual probability of occurrence. So as you can see here, we have a base station antenna which is serving two different users, and there are two obstacles or buildings in their path, and one of them has line of sight path and the other one has non-line of sight path. So essentially for both of them, effectively the overall average path loss can be described by using the probability of existence of line of sight path or non-line of sight path between the base station and that corresponding user. So the question now comes is that if we can describe the path loss in this manner, how do we model the probability of existence for individual propagation groups? To this effect, in ITU the document, International Telecommunication Union's document, it has been listed the different factors which can influence the line of sight probability. The first factor that can influence line of sight probability specifically, which it is for the urban environment. These are man-made blockages, which essentially refer to different buildings or different buildings or artifacts that are placed placed in this environment. So they specifically depend on the size and locations of the buildings, building heights and areas. They actually decide the presence of the present buildings effect on the LoS path. And in some recent works, it has been shown that it can also be we can model these particular effects using random shape theory. There is also another effect, which is the distance between the transmitter and receiver in the ground or the terrestrial distance, and because it determines the number of possible blockages in this path. As a matter of fact, since there are blockages always present in an urban environment, the longer is the distance between the transmitter and receiver, the more number of possible blockages that will be present, and the higher is the probability of blockage of the LoS path. Of course, we also have to account for the antenna heights and of the transmitter and receiver, as well as the variation in the terrain when we talk about LoS probability. There are two currently existing models of determining the LoS probability mathematically. The first one is the ITU-based model. The other one is the random shift theory-based model. For our work, we are going to follow the ITU-based model. In the ITU-based model, a statistical description of various blockages or buildings that are present in the urban scenario has been developed. And it has been developed using three statistical parameters. The first parameter is known as the ratio of the built-up land area to the total land area. The second parameter is given as the average number of buildings per unit square kilometer area. And the third one is the scale. It describes the scaling parameter for building height distributions. And in ITU model, Rayleigh distribution has been assumed for representing the building height distributions. Based on these statistical parameters, the average number of buildings in a ground distance R on a link between any transmitter and receiver has been characterized as this expression M, which is essentially the floor value of R into root over of alpha into mu. In ITU model, the variation in terrain is not considered in general. However, it has been stated that it can be accounted for by using an offset to the blockage height using the Stadium's model statistical properties. Using these various statistical parameters, in the end, the line of sight probability for ITU model has been given by this equation, where we characterize the blockage probability for individual buildings that are present on the link, and in terms of their individual distances, and as well as the height of the transmitter and receivers. However, this model has one small weakness, is that in determining this line of sight probability, the different blockages that are supposed to be present between the transmitter and receiver has been placed at a uniformly fixed distance away from the transmitter or receiver, and as a result, computing this line of sight probability, it does not give us an explicit expression which can be used for tractable analysis. So a further modification of this line of sight probability is required to understand the influence of antenna and building heights on the blockage. So if we look at the scenario where we have a base station and a user, and there are several buildings between them, and they are separated by distance r, we can actually mathematically characterize the entire probability of blockage of the line of sight path for their specific antenna heights and their building heights. The idea was that to assume that building height is always higher than the user antenna height, and Of course, we are using the Rayleigh distributed building height distribution from the ITU model with the scaling parameter gamma. We are also assuming that building width is 0, which means that on a single line of link distance, the blockage of line of sight paths, they are processed online, and so we don't look at we can look at a 2D reference frame to understand whether a building is going to block a line of sight path between the base station and the user, and it can be calculated to show that this blockage probability is independent of the distance of the blockage from either the base station or the user, and can be given as the expression as a function of the scaling parameter of the building height distribution, as well as the individual heights of the base station and the user antennas. Using this particular model for blockage probability, we can simplify simplify the line of sight probability model for ITU scenario as simply 1 minus rho b to the power r into root over of alpha u, where r into root over of alpha u represents the average number of blockages present in the network for between the on it over a link distance r, and 1 minus rho represents the base probability corresponding to individual blockages. If we plot this line of sight probability expression as a function of ground distance, what we see is that as we reduce the distance between the transmitter and receiver, the line of sight probability increases almost exponentially and converges to 1, which essentially shows that if we consider the traditional cellular systems where the distance between the base station and user is significantly large, it is sufficient to just assume that there is effectively no line of sight path. However, if we are increasing the number of base stations or number of access points, thus reducing the distance between the base station and user, it would be prudent to assume that line of sight paths are present. This essentially works as a motivation for us to understand the effect of line of sight and non-line of sight paths being present in a self-free massive MIMO systems. With this introduction, let us first take a brief look at the wireless channels and how we scale up traditional MIMO systems and go to the self-free scenario. And then we'll discuss the performance in realistic LoS and NLoS channels. As we have already discussed, the initial problem of single antenna systems in wireless channel is the fading due to multipath propagation, which leads to severe degradation of the received signal power, resulting in the channel being in deep fade, and it causes outage. And it also reduces the reliability of our transmission. One such solution that was provided was to implement diversity, which is essentially introducing controlled multiple paths and then jointly detecting these multiple copies of received signal received from multiple paths and multiple paths to improve the reliability and coverage. Among the various diversity techniques that have been developed over the years, time diversity, frequency diversity, and space or antenna diversity are the most popular diversity strategies. In this case, we are talking about MIMO systems, which is essentially space and antenna diversity. The space and antenna diversity, it can essentially be classified into two categories: receiver diversity and transmitter diversity. In the transmitter diversity, when we are implementing transmitter diversity, we are essentially calling it a MISO system, where there are multiple transmit antennas at the transmitter point converge, and the signal is converging to a single antenna at the receiver. And what we are performing is essentially precoding of the signal or beamforming. On the other hand, in receiver diversity, we essentially call it a CMO system, where we are transmitting a single antenna from a single antenna and that data and that signal is received at multiple antennas, and using the assumption that all these antennas are sufficiently far apart to provide independent channels, we can obtain diversity gain as far as large as L, as large as the order of the antennas, as well as we can improve the capacity of the system by increasing the received signal power gain to the same level of the large number of antennas. And it can be shown that the asymptotically we can obtain a 3 dB power gain with every doubling in the number of antennas. Now, when we combine both this transmit diversity and receive diversity, we obtain a point-to-point MIMO system where we have channel knowledge both at the transmitter and receiver. And using singular value decomposition, we can resolve the entire channel matrix into a set of parallel channels, resulting in a spatial multiplexing gain. From point-to-point MIMO system, we can finally approach the multi-user MIMO system, where each receiver may contain one or multiple antennas, and no inter-user, and without considering no inter-user communication, we can assume a multi-antenna transmitter is serving one or more antenna enabled multiple users. And usually we assume the number of transmit antenna far exceeds the number of users or number of user antennas. Now, if we increase the number of antennas in the MIMO system, we essentially obtain a large-scale antenna system if we keep on increasing the number of antennas. And the more number of antennas are there, the larger is the number of data streams that can be processed. And with the increasing number of data streams, using the law of large numbers, we can essentially see that the channel power gain can become deterministic in nature. This is known as channel hardening, which is one of the key features in massive MIMO systems. In massive MIMO systems, we are essentially implementing hundreds of base station antennas for tens of users, thereby obtaining a huge gain in energy and spectral efficiency. If I look at the ideal massive MIMO configurations, we can summarize it as having a K single antenna users and M antenna base stations. So in this way, the uplink of massive MIMO systems is essentially a CMOS system, while the downlink can appear as a multi-user MISO system, and the channel matrix is assumed to be known as the base station only. And because of because of channel hardening, we can see that individual data streams from each user can be obtained as having almost a deterministic power gain. Furthermore, the TDD-based transmission in uplink and down, we also consider a TDD-based transmission in ideal massive MIMO, which essentially also is followed by uplink and downlink channels reciprocity. And it requires combining at the base station, combining of the data at the base station in the uplink and precoding for the downlink. And it can be shown that asymptotic power gain with imperfect channel knowledge results in an order root M, which is where M is the number of antennas, which is essentially 1.5 dB improvement, performance improvement, even with every doubling number of antennas. So key takeaway from massive MIMO is that we can use the simple channel knowledge based combiners to achieve high performance capacity. Linear combiners can be successfully used with sufficiently large number of antennas, and at very large number of antennas in maximum ratio combining, zero forcing, these type of linear combiners, they have their performance converged. And similar simple precoders can also yield similar performance in the downlink. Now, if we look at the future in TDD massive MIMO, we can say that it is built with a cellular concept at the base. So it is suitable for large cells and can act as a backbone network and can act as a backbone for heterogeneous cellular networks. It can also use millimeter wave front-end transmissions for hybrid precoder structure, and also act as device-centric architecture where it can integrate edge or fog computing services. Of course, there is also native massive MTC services where grant-free random access can be implemented using massive MIMO systems. So the question comes: is there anything cell-free massive MIMO cannot do. If we look at the basis of the cell-free massive MIMO, if we look at the basics of cellular massive MIMO, it is built on the traditional concept of cellular networks. So the same weaknesses of cellular networks are also present in cellular massive MIMO, which is that the service is still not very good at the cell edges, and uniform service is everywhere is impossible. Furthermore, if we consider edge computing or any other innovative processing which requires providing service to myriads of devices at minimum delay, it is still an elusive dream in cellular massive MIMO networks. Here, the cell-free massive MIMO or distributed systems for massive MIMO comes into picture. It distributes the antennas across multiple access points throughout the network and provides a user-centric service approach, which is similar to network MIMO systems. Besides, it provides a centralized joint processing at the CPU, which can significantly improve the receive signal power for processing. If we go to cell-free massive MIMO from conventional MIMO systems, and if we compare the performance with the conventional small cell networks, what we see is that cell-free massive MIMO systems can provide a uniform coverage, or better yet, we can say that it can provide a uniform set of rates for all the users, which is not always the case for the small cell systems, especially when we look at the small cell systems at very low data rates. However, with this introduction, we can now talk about or summarize what are the key takeaway points in cell-free massive MIMO systems. The first one is that it promotes a geographically distributed antenna systems. It provides a centralized processing unit, which is essential for achieving power gain and diversity gain. And it also makes localized access points so that it makes more of a network like itself, and it can provide ubiquitous service to everyone through its distributed localized resources. Now, as I said, that these are all the results that have been provided or that have been derived based on the assumption that there are always in non-line of sight paths between users and the base stations, which we have already seen that is not always true in practical scenario. So the main goal of our work is to see what happens if we consider a probabilistic presence or randomized presence of line of sight and non-line of sight paths between base stations and users in a cell-free massive MIMO systems. For this purpose, we are considering only the uplink transmission case for a cell-free massive MIMO system, where there are k single antenna users and m access points, each equipped with n antennas. We are also assuming the access points are equipped with uniform linear arrays of antennas with antenna spacing d. See, there's other system parameters that we can consider between the mth AP and the kth user are the individual user and AP antenna heights and their corresponding link distance and the path loss. For the path loss, we adopt a very simple model with a specification to the with a specific assumption to compensate for the near field path loss. And this approximation and this path loss model and this common path loss model, it consists of the link distance and the reference distance as a ratio, and eta represents the path loss exponent. The link distance is a three-dimensional link distance between the access point and the user, which consists of the ground distance dmk between them and the difference in their antenna heights. For the channel between any access point and the user, we consider two different components. The first is the multipath fading component due to non-line of sight propagation, which is the fast fading component. We consider it to be Rayleigh distributed and independent and identical for each of the independent and identically distributed for each of the access points. The other part is the channel for line of sight propagation, which we define to be dependent on the angle of arrival of the signals at the access points. And we also incorporate the antenna gains between the transmitter and receiver. We also consider a parameter for existence of the line of sight link, delta mk, which essentially provides that essentially can be summarized as the probability of delta mk being 1 as the line of sight probability. With these three parameters, we can now present the complete channel expression, which consists of both the line of sight component and the non-line of sight component. And the line of sight component can be given by this expression, where we also account for the different antenna gains at the transmitter and receiver, as well as the vector of angle of arrivals for all antennas at the access point. If we now plot, we also plot the presence of number of line of sight existence of the number of line of sight paths for any typical user from different access points, and we can see this probability mass function. It varies from different configurations of the access points that can be deployed for cellular selfie massive MIMO systems. We see that when we have 128 access points at the selfie massive MIMO system, almost 60% of the AP user links do not have any line of sight component, which means that at least 60% of them have NLoS channel. While if we keep on increasing the number of antennas, we see that this probability keeps on decreasing. And for m is equal to 1024 access points, we see that there is less than 5% probability that the channel between access point and user will be non-line of sight. This essentially shows that as we increase the number of available access points in a selfie massive MIMO system, there will be higher probability of having line of sight paths. So, and since the line of sight paths, they have less path loss and higher power gain, the overall coverage of the entire system will improve far more significantly when compared to all non-line of sight channel. So based on this motivation, we now first perform the channel estimation, which is the traditional linear MMSE-based channel estimation with k orthogonal pilots. We do not consider any pilot contamination, and using these k orthogonal pilots, we obtain a linear MMSE estimate. A linear MMSE estimate in terms of the covariance matrix of the channel. And using this channel estimation, we perform conjugate beamforming and consider the achievable date of a typical user or the kth user at the selfie massive MIMO system CPU after we consider the signal accumulated in the CPU. And what we observe is that we obtain a very complicated expression which looks like which is obtained as which gives us the lower bound using the Jensen's inequality. And in a similar fashion, we also obtain an upper bound by simplifying the receipts by simplifying the achievable sum rate by using the ratio between the function between the GKK hat and its corresponding average value. In a similar approach, we also obtain the joint decoding performance, and for which we consider the lower bound and upper bound on the achievable dates. What we ultimately see is that when we plot these different achievable dates and compare them with existing works on ubiquitous availability of LoS channel, what we see is that the ubiquitous availability of LoS channel or Ricean channel-based analysis does not actually correspond to the practical performance of the selfie massive MIMO system. In the very low SNR regime, what we observe is that due to the presence of all LoS channels, the actual performance of the Raytian channel, the actual performance based analysis based on Raytian channel, it provides much higher achievable sum rate when compared to our proposed LoS probabilistic LoS and LoS channels. And at the high SNR regime, because of all LoS channels, there is a significantly larger amount of interference, which causes the sum rate to saturate. On the other hand, with our proposed channel, due to the presence of both LoS and NLoS channels, we can still see that the actual performance of the self-massive MIMO with our proposed channel keeps on increasing. So in short, the Raytian channel or ubiquitous LoS channel-based assumption underestimates the performance at high SNR regime and overestimates the performance in the low SNR regime. So in short, it cannot be used to model the self-massive performance for practical realization. We also provide a we also have provided a validation of the analysis of our achievable date as a function of SNR, and we see that the lower bound, both the lower bound and upper bounds correspond to very closely to the actual simulated data. Now, if we focus on the AP antenna distribution, access point and antenna distribution, which is one of the significant aspects of self-massive MIMO systems, then for both interference limited channels and noise limited channels, what we observe that some of the users have very low received SNR values, while some of the users have a very significantly high SNR values. This is essentially separates out that depending on the now available number of access points, some of the users will have line of sight path and can therefore achieve a very high receive signal to interference and interference power ratio, while some of the users which do not have any line of sight propagation component, they will have very small receive power. This essentially leads to a capture of the entire system by the users with line of sight propagation component, preventing us from achieving a uniform service for all users. And we also see that as we decrease the number of access points, this deviation from the uniform service capability keeps on increasing. So one thing is for sure is that with self-massive MIMO systems, unless we are planning on distributing all the antennas to each of the access points so that we have single antenna access point everywhere, uniform service is not guaranteed. Finally, if we plot the sum rate performance for conjugate beamforming, centralized MMSE, and joint decoding, what we see is that in the perfect CSI scenario assumption, the MMSE-based performance closely approximates the joint decoding performance, which essentially shows us that with a relatively low complexity MMSE combining, we can achieve the joint decoding we should be able to achieve the joint decoding performance in self-massive MIMO. However, when we add the LMMSE-based channel estimation component, we can see that the performance significantly worsens as we increase the signal to noise power ratio. This essentially shows that a simplistic channel estimation technique like linear MMSE cannot perfectly model or cannot perfectly reduce the error component in the channel estimation, and so better channel estimation techniques is required for this new LoS and NLoS based channel. Finally, we also present the different access point configurations and their corresponding performances for self-emissive MIMO systems. And we observe that as we increase the number of access points while keeping the total number of antennas in the system constant, there is a significant increase in the performance when compared to the scenario where we were deploying multiple antenna-based access points. So in short, we can say that single antenna access point is the best possible scenario in self-emissive MIMO. And we can also say that if we are going to consider typical NLoS-based channels, which it cannot be trivially extended to the line of sight or non-line of sight channels. So in short, we can conclude that uniform service to everyone is not innately achievable in all configurations in self-emissive MIMO systems. The best possible performance of self-emissive MIMO is achieved when all APs are having single antennas, and we need better techniques and algorithms for which are required for practical performance analysis and uniform service capability in self-emissive MIMO. With this, we can also consider a few of possible extensions in the direction of user-centric self-emissive MIMO or downlink performance optimization with power control, or studying the impact of various off-device computing services in like edge computing and caching in self-emissive MIMO systems. Thank you.
Thank you, Dr. Mukherjee, for an informative talk. We can take a few questions now.
Hi, Professor, I have one quick question. For
Yes.
that result, that single antenna AP is the best. How many users are considered in the system?
64 users.
Okay, in 1 kilometer across 1 kilometer area.
Yes.
Okay. So is it true also for very small number of users?
For small, we have also verified the result for small number of users and increasing the number of users. But the results are coming out to be same. The only difference is that there will be difference in performance due to increasing number of users, which is actually causing more interference. Other than that,
so the entire processing is like centralized processing, means APs are not doing anything like designing local preferers or something.
For conjugate beamforming, the APs are performing the local processing, but the joint data, but at the end, the CPU is combining all the data to perform the detection.
Okay.
For MMSE and joint decoding, we are considering centralized processing.
Okay, yeah. So for that means for that MRC case, is channel hardening also assumed for single antenna?
No. We are not specifically assuming any channel hardening.
Okay.
You see in self-emissive MIMO, channel hardening can only be achieved if we have multiple antennas at each of the APs, right?
Yes. Yeah. Okay. Thanks. Yeah, that was nice.
Are there any other questions? If there are no more questions, let's end the session. Once again, let's thank Dr. Mukherjee. As discussed before, we would like to remind the audience to subscribe to our Google Groups, which is the mailing list for information on future talks. You can also visit our website for more details. The links have already been pasted in the chat box. The link to the recorded video will be also posted on the webpage. Thank you and have a great evening.